So, good morning, my dear student. As in my first lecture, I had discussed the salient features of the Debye-Huckel theory, and I had discussed the history of Debye-Huckel theory. Today, in this particular session, I will give the special emphasis on the derivation of the first part, that is called the Debye-Huckel theory. And I would like to discuss the role of electric potential as well as the charge density and thickness of ionic atmosphere. In my first lecture, I had given you the complete references of this Debye-Huckel theory. So today I will not repeat all those things, but as you know that if you see the literature, if you see the internet, if you see the NPTEL or e-Pathshala, you will have large number of information about this most important Debye-Huckel theory. But frankly speaking, that my today's derivation is based on an introduction to electrochemistry by Samuel Glaston. And I have also referred the original research paper of Debye and Huckel, which was published in, of course, in German language in 21923, 1923. But fortunately, the English translation is also available. So I have taken some of the information from that English translation by Michael Brous 2020. In addition to that, because and that day I told you that for derivation of the Debye-Huckel theory, we have to take the help of some simple mathematics as well as electrostatics like Poisson's equations, then statistical thermodynamics like Boltzmann distribution statistics, and a simple mathematics, simple algebra. So I have taken some of the information from literature also. So, but basically, as I told you, that the complete derivation is based on, mostly based on this Glaston. Now, you know that, and it is quite simple, that Peter Debye and Huckel actually proposed this important theory of strong electrolytes. And what I have done, that I have divided my lecture into three parts. That day I also told you that it is very big and all are interrelated. You have already studied the Kohlraasch law, you have already studied the Oswald dilution law. So for clarity and novelty and for the convenience for the student, I have divided my derivation into three parts. And today I will concentrate only the first part, that is the fundamental part, Debye-Huckel theory of interionic attractions. And I will derive that equation. I will explain what is D is dielectric constant, what is kappa, it is just like a K, it is kappa, what is the relationship between the thickness of the ionic atmosphere, what is electrical potential, charge density. And once you understand this first equation, then you can very easily solve the second part, that is called the Debye-Huckel limiting law, which gives the relationship between the activity coefficient, mean ionic activity coefficient, and ionic strength. And if you understand this first theory, then you are also able to calculate the last equation. Onsager slightly modified that equation. That is called the Debye-Huckel-Onsager theory. Now see, the final equation is different. This is the first equation is different. And you can understand one R is there. Here no R is there. This is Debye-Huckel limiting law and this is Onsager equation. If you see Kohlraasch law, just you remember that molar conductance at particular concentration, molar conductance at infinite dilution, and there are two constants. And of course, it is related to the concentration. So it is very simple thing. So today I am just doing the first part, how we study the interionic attraction and the demerits of the Arrhenius theory, why there is a deviation in the non-ideality. That is the my purpose. Now, whenever we talk about this interionic interactions, so I have to take the help of two important laws. Number one is, I will explain that why it is called sometimes Poisson-Boltzmann equation. And then sometimes we also call it linearizing Poisson-Boltzmann equation. Mathematics students can very easily understand these things. And first part is the Boltzmann distribution. And this is of course related to Debye-Huckel theory, the relationship between the free energy and other things, activity coefficient and other things. Now this picture is the most common picture and it is available in all the internet. I have taken from Wikipedia because you know that most of the students understand that suppose there is only one generally we consider that it is not 100% true. Suppose we are talking about the strong electrolyte sodium chloride, NaCl. And of course, this is most of the ions are spherically symmetrical. So it is an assumption that one is central atom, central ion, and it is surrounded by the, but it is not like that. In addition to electrostatic attraction, there is a thermal motion, or that is called the thermal movement. So it is not necessary that always most of the ions follow same behavior. There is a possibility also that this is central, but it is quite obvious that if the central ion is negatively charged, so the surrounded atoms is oppositely charged. That is there. And it is not just like a very symmetrical structure. Although for mathematical calculation, we have to assume that it is symmetrical, spherical, symmetrical things. But it is not like that. Maybe you can call it a ionic clouds, complete large number of ions. There are some scattering. And most important thing, water is there. So suppose there is a possibility of many water molecules are there. So maybe there may be electrostatic repulsion is also there. Maybe there is a electrostatic attractions and other things. And so it is very difficult to calculate this thickness of the ionic atmosphere, or sometimes it is called the ionic cloud. So what we do, generally we assume that there must be some point, central points, and suppose it's infinite, because that is most important. We have to consider a volume element and the distance is r. So why we are taking the help of the thermodynamics, statistical thermodynamics, because we do not know that what is the condition, the fraction of ions surrounded by the central atom. One times it may be cation, maybe positive ion, maybe the negative ion. So therefore we need the statistical thermodynamics, Maxwell or Boltzmann distribution, total number of ions present. And then of course if you are talking about the ions and movement, other things, so there must be some electrostatic potential is also there. Then charge density is also there. So it is very simple. In the first part, we'll study that how that electrical potential is changed due to these things. So this is a very common type of diagrams you see. In some books you see there is a complete dark because it's a cloud. You just write like that. It's a cloud type of things. But for mathematical derivation, we have to think for these things that we must consider that suppose this point is A, and we consider that this is an ionic cloud, and because we solved that statistical thermodynamics, so we think that there may be some n plus positive ions and total number of n ions, negative ions, okay. And that volume element, which is very important, where we will consider the electrical potential, or sometimes it is called the electrostatic potential, then we will calculate that after this thermal movement, the average number of positive ions is dn, very small, and dn plus. So we have to calculate, and you know that statistical thermodynamics is very simple. N dash is equal to n exponential E by kt. That is thing. So we have to perform some of the work in order to bring a unit positive charge from infinite to this thing. And it is quite natural if R is infinite. So naturally the question of thickness of the ionic atmosphere maybe decreases. So it depends, the R is a very important factor. Okay. Now as you know that whenever we study any type of equation, so there are some postulates, there are some assumptions. You may agree or not. So similarly, in Debye-Huckel equation, there are some postulates. Number one postulate is, you all know that because this is the difference between the strong electrolyte and weak electrolyte. Here we are considering the strong electrolyte, so there is a complete dissociation of that, whether it is the sodium chloride or potassium chloride. Second assumption is that it is a solution is very dilute, as I have already told you. I have already told you the concept of the ionic atmosphere. Now, most important point is that the ions are considered as uniformly charged hard sphere, because we consider it for mathematical derivations. And of course, if there is a positive ion and negative ion, so definitely there is a question of Coulomb's law, that is you all know, a very fundamental thing. Coulomb's law is follows, and if there is two charge, so Q1, Q2, R. So R is very important. And suppose there is a cloud of positive ion, there is a cloud of negative ions, and of course it is electrically neutral, so I have to calculate the charge density also. Suppose one charge is valency is Z plus, another is Z minus, electrical potential is epsilon. So I have to calculate the charge density, number of ions per unit area, per unit volume, and other things. So if I am able to solve, if I am able to correlate a relationship between the electrostatic potential and charge density, my 50% problem will be solved. You follow my point? So it is so simple thing. And of course, now it is clear that this deviation from the ideally, that was the problem of Arrhenius or Oswald dilution or the Kohlraasch law, now it is 100% confirmed that there is a Coulombic force of the attractions. And of course, the dielectric constant of the medium plays a very, very significant role, because if you change the solvent, yet thickness of the ionic atmosphere will be changed. If you change the temperature, the thickness of the ionic atmosphere will be changed. If you change the valency, in place of univalent electrolyte, you will take the unibivalent electrolyte, If you change the concentration, at the last of this derivation, you will be able to answer all those questions. The role of temperature, the role of dielectric constant on the ionic atmosphere. Okay? So, how do I solve this thing one by one? I have already told you that first I will see the charge distribution of the ionic atmosphere. Again, it is the question of statistical thermodynamics. Fraction of dn plus or dn minus present per unit volume. So, therefore, naturally I have to apply the Boltzmann distribution. Second, I have to club with this Boltzmann distribution with that Poisson equation, and it is nothing but the relationship between the electrostatic potential and the charge density. And once I calculate this relationship, then of course this is the second part, the expression of the electrostatic energy, and it is Debye-Huckel limiting law. So I will not discuss today mean ionic activity coefficient or the Helmholtz free energy. I am just starting the derivation. Now the derivation, again, many times I am speaking the same thing, but for the student purpose, just you, whenever you solve any big derivation, it is a physical chemistry concept. If you understand the basic concept, you can very easily derive any complicated equation. Don't worry whether you are a biology student or a mathematics student, but you have to understand the basic concept. So there are only two parts. First, we will use the Boltzmann law of distribution. Why? Because calculation of the electrostatic potential contributed by the surrounding ions. And then I will calculate the electrical charge density. And for electrical charge density, we have to put the value of this Boltzmann law of distribution. And then once you calculate this thing, then we will use that very simple equation, Poisson equation of the electrostatistics. You all know this equation is not at all very difficult. Laplacian operator, electrical potential is equal to minus 4 pi charge density divided by dielectric. I will explain this thing. So, just keep in mind that there are only two parts. First part, again and again I am saying same thing, use of Boltzmann law of distribution statistics, and second, the role of Poisson equation. You just correlate it and you will get the final equation. So let me start with the first. So this is the first derivation that here I am consider one positive ion in the central, and it is surrounded by the negative ions, and due to a thermal motion there will be a change. So it is a probability. There is a possibility that in one time there is a large number of positive ions in one side, and another possibility is also there is a probability of the large number of negative ions like that. And for that we have to calculate the net charge of the ionic atmosphere. And it is quite natural, if it is very near to the main point, so the charge density is greater, and if it is far from central part to this part, so naturally the charge density will be low. So I have to calculate charge density due to positive ion, charge density due to negative ion. Suppose now we have started this first point. So you must know the symbol I used, like left side. I think red is better. So I will use two symbols. First is the valence, you all know, Z plus Z minus, I'm just considering the univalent or one. N plus, N minus, total number of ions. Dn is the total number of negative ions present in the volume element, and this psi is the electrical potential. Sometimes it is called the electrostatic potential. Now, work required to bring a positive ion from infinite to that thing. So I deliberately have Z plus charge and potential. Similarly, if it is a negative ions, so it is quite natural. Yes, this. And you know, it is very simple. The after n dash, then n, actual number of ions present, exponential E by K, energy and kT. K is the Boltzmann constant. Okay. Now, in order to avoid any confusion, in some books you will find the total number of is n, but in full derivation, I am using small n for number of total ions and small n number of total negative ions. Okay, so I am not using capital N. So there are two concepts. One is for very simple, you can write that dn, because I have types, so please check it. Sometimes maybe positive superscript and subscript. So this is in volume element, actual number is n, exponential minus, okay. In this case, the work and energy is actually, if it is Z, so Z plus, very simple, charge, electrical potential, K and T. Don't write K, B, you can write also. It is actually Boltzmann constant. Okay. So first you write the, for positive ion, second you write the negative ions. Concept is same, but in place of Z plus, we will write the Z minus. Only when we solve it, so here is minus also, here is minus, one side plus, one side. That means if I consider E sin k2, so I will get what I get, minus x minus 1. I am just using this part. If I consider x is equal to E psi divided by kt, in one case it is, because minus minus plus, and one case it is plus. Everything is same. So it is clear. Second part. Now we are talking about the first part is over. Apply simple Boltzmann distribution statistics. There is no confusion. One for negative ion, another for the positive ion. Now second part is the use of charge density. So it is also same thing, one for positive ion, difference between positive and different, and then I have to substitute the value of Dn. That's all. So you see, this is the first part for positive ion, and second part this. Only difference is that this is a volume element, but whatever we are calculating with respect to charge per unit volume. So therefore I am just using the very small changes. Now very simple, substitute the value of Dn, actual number of positive ions present in that volume element, in the charge density equation. Substitute the value of Dn. We have already calculated. So very simple, you see. This is common. So N, Z for positive, and this is Boltzmann distribution, minus for negative ions, this is for negative ions. Suppose for mathematical simplicity, just see it, very simple. For mathematical simplicity, because if I consider one for sodium ion, another for chloride ion, another thing, or suppose barium sulfate or something, there will be a problem. But it is not like that. This equation is only valid for univalent electrolyte. This equation is valid for any types of strong electrolyte. But in order to achieve a final equation, we are assume that it is univalent. And that means if it is sodium chloride, so you know the valency suppose is Na plus and Cl, so it is 1. So I can use simply Z. Similarly, again it is as if it is not like that. The total number of positive ions is exactly equal to total number of negative ions. But again, in order to achieve a final equation and to become a very simple equation, so N minus N plus are equal N. So two things common. One is N, number of either ion, positive or negative ion, and another is the valency. So you see this is common, N, epsilon, Z is equal to 1, so no problem. Now epsilon 1 is, why it is minus? You follow this point? Very simple. And here it is plus. So I am getting a very simple equation. Charge density is equal to N, number of any ion, cation, charge, whatever the charge, exponential is minus x, second is exponential plus x. You can sit there. When there is a small, you can come and then focus your camera. So up to this is clear or not? I am using very simple derivations. Now again, if you are not a mathematician, don't worry for that. It's a very simple thing. Because you know, Kusi Srivastav can very easily understand. Our objective is to solve this problem. And this is a point, central point, and here is the volume element. And I have to consider this number of ions and other things. So how do I solve these things? So you know that there is a simple system expanding the exponential. Very simple. If there is a fundamental rules is that 1 plus x, x2 factorial. I have taken from literature. It is for the biology students and other things. And in case another is the 1. The same thing you see. 1 minus x and then x square to then minus like that. And you know that if I ignore, if you are a true mathematics student, so don't worry for that. You have to solve whole equation. That means if it is 1 minus x, so I can write 1 minus x, you see. Then like that, you can like that. But for simplicity, I am ignoring the higher orders. Because the value of, if you consider these E psi by kt is equal to x, it is very, very less than 1. But if you are a true mathematician, no sir, I don't want to delete all these things, I will solve it. You can. You can. But for simple student, just don't worry for that. E exponential minus x, so 1 minus x, like that. Minus 1 plus x. Okay. So 1 cancel. So it is minus 2x. It is minus 2x. So and n is already there. N is already there. So this 2, then n is x. So this sign is there, and this epsilon is there. So square. So what I am getting? This simply final equation. If you are not happy with this equation, you just minus it from this. So you will get x square 3, x 5 like that. But don't worry for that. So your 50% work is over, that you are getting the actual charge density per unit volume is nothing, 2n, maybe plus, maybe minus, epsilon square, and this Boltzmann constant. But this is, we assume that it is a uni electrolytes, and it is very, very dilute, but it is not like that. And you all know that for any type of electrolyte, we can calculate the ionic strength, that is half summation Ci Zi square, the concentration of the electrolyte, concentration of ions, and the valency of the ion. So that is called the ionic strength equation. So now we are happy that we have already derived the equation. Now we can apply these things for any types of the electrolytes. So I just use add. Now you know minus is very important, because 1 minus x plus, that is minus 2x. So therefore always there is a minus. So I can write E square, epsilon square, psi is the electric potential, Boltzmann constant, and summation Ci Zi square, half these two to cancel. So I am getting the final equation. Now my first part is over. That I am getting, I mean Debye Huckel, they have derived the equation where charge density can easily be calculated, minus epsilon square psi kT summation Ci or Ni here, because we are talking about the number of ions. So therefore Ni Zi square. So the first part is over. Is it difficult? Not at all difficult. Now just round this. Now what should be the second part? Tell me, what should be the second part? Now you have a equation where you got the charge density and sign. So what should be the next part? Anybody? I have already introduction part, I have already told you. Khushi Srivastava. What should be the second part?
So determining the electric potential.
You have to determine, or you have to understand the relationship between charge density and the sign, electric potential. And there is the equation, thanks to the physicists, that they have derived an equation that is called the Poisson's equation of the electrostatic, because we are talking about the interaction. So naturally there are two terms, electric density and the electric potential. So the last part is very simple, that we have to apply the Poisson equation and substitute the value of this charge density. Then we will get the final equation. Okay. So deliberately I am just deriving this equation in a simple way so that the student can understand. And I thought that today I will discuss only first part, then another class second part, then the third part. And there should be no confusion for the students. Now, last part. First part is over. We are using statistical thermodynamics. Now, relation between the electrical potential and the charge density. And is a universal equation. And that is called the Poisson's equation of electrostatic. And suppose it is, again for mathematics students, because it is a volume element, so there may be x direction, y direction, z direction is possible. Because it is very difficult to which directions, it is not like that here ions here and here. So Poisson's derive an equation for rectangulars where there is a x direction and the y direction and z directions. And the equation is that Laplacian operator, that time, because we are taking the electrical potential, so I must write like that, psi electrical potential is equal to minus 4 pi, and charge density is D is the dielectric constant. D is the dielectric constant. And it is of course related to Coulomb's law of force between the electrostatic charge. So because there are three directions, and so I can write like that, del square sine dx square, okay, plus del square sine d del y square plus del square sine dz square. So here you can write like that. Like that. Because they are a three-dimensional Cartesian coordinate. And our system is Is it rectangular? No. It is spherical. So, and again, mathematics students can understand many times in quantum mechanics also, particle in a box, in 1 dimensional and 3 dimensional. We have to change, yes, from Cartesian coordinate to the polar coordinate. And if you are, I'm not going to discuss the whole things we need, and there are 3 variables r, theta, phi, angles, and other things. But fortunately, that ionic atmosphere and that central charge and is only depends upon the r. So if you want to write the complete equation, don't write the complete equation. That this is for the conversion of Cartesian coordinate to the polar coordinate for spherical things. So 1 by r square d by dr, r square d by dr, then you know d theta is there, d phi is there. There are so many things. But again, fortunately, it is only depends on this r. So I can delete, I can d theta, d psi by d theta or d psi by d phi angle is not required. So therefore, I can only concentrate only the first part of that Poisson equation. It is not related to the Debye-Huckel equation. This is a fundamental equation of the Poissons. But I am applying this equation because this relates the electric potential and the charge density. So I have to just substitute the value of charge density in that equation. That's all. So therefore, I am using the use of this Poisson equation and not complete equation, only that part. And so what should be the, because d psi by d theta is 0, not required, independent of this angle. We are only concentrate only on the r. So therefore, because I do not know, I am not expert in the computer system, so I have taken from literature these things. Actually 1 r square, the first part I have taken, d by dr, you can write like that, very simple, r square, last part, just within 5 minutes I will finish these things. So this is the equation, and don't worry that there is also a minus sign time. So you see why I have chosen this equation, because it is only for spherical coordinate and only r is changing. Okay, so you can, if you forget everything, you can just write these things. And deliberately I am using d is the dielectric constant, I am using the Glaston, because in some book there may be some confusion that epsilon is also sometimes considered as the dielectric constant in some books, maybe some research paper. But I am following that Glaston book. So here is dielectric constant is d. So you must write here that d is the, therefore deliberately I have written here dielectric constant. So there will be no confusion. And this k is the Boltzmann constant and T is the absolute temperature and other things. So the last part of this equation is that, so 1 by r square d by dr, r square d by. I am not going to discuss the how you got this value, Cartesian rectangular coordinate. No, you just directly you can write these things. And this is equal to 4 pi rho and d. And you know the value of rho is epsilon psi by kt, because I am not z square. Yesterday Abhishek was absent, so myself prepared all these things. I am not expert in the computer writing or latex and other things, so there may be some problem. So you can write like that. So, epsilon square psi kt summation ni zi square. So last part you substitute the value of here. So first part is that minus minus, so you can write 4 pi epsilon square d kt, kt is lower side, kbt summation Ci Zi square. So this is our final equation. Again, there is no doubt what I am doing. I am doing nothing in the place of this charge density. I am writing this whole value. This, so this is there. Okay, 4 is already there. Minus minus cancel. Ci Zi square and this. You can remove these things. Or should I write like that? Psi is also there. Na? The psi is also there. So what I can do? I write, suppose K is kappa square into psi. So this equation is a second order differential equation. So in place of this, why I have written K square, that means whatever I will write, it must be under root like that. So again I am just repeating these things. We have already determined using the Maxwell-Boltzmann distribution of molecular velocities, Maxwell-Boltzmann statistics, the charge density. If you forget anything, just you remember these things, and directly, if you don't, you can simply write Laplacian operator is equal to minus 4 pi. You just substitute this value, whole value. So you are getting 4 pi is this value. So I am just writing these things. Now this. So therefore K is equal to, I can write like again 4 pi dielectric constant kBT summation Ni Zi square. Why it is half? Because I have written here kappa square. This is the most important part of this thing. I will tell you what is that. Ultimately, what we are deriving, because again I am saying the same thing, if it is a central part and is R, is a volume element, so this thickness of ionic atmosphere is very important. So this 1 by kappa, it is not observed conductance or specific. 1 by kappa is called thickness of ionic atmosphere. Thickness of the ionic atmosphere. So with that, now it is called actually Poisson-Boltzmann linearized equation, because we are using Poisson equation and as well as we are also using the Boltzmann equation. So therefore sometimes it is called the Poisson-Boltzmann, linearized Poisson-Boltzmann equations. Now I have to determine that what is this kappa and other things. So the last part is that. So we are getting again the same equation. Now because it is a second order differential equation, that means you know kappa square and psi. So how do I solve this equation? Again, mathematics students can also easily understand these things. You know that most of the differential equations there is a solution that can be. So the solution of this second order differential equation is like that. Psi is equal to, because there are two possibilities. A by R exponential minus kr plus, in some books it is written like A dash, A double dash you can write, but here I am writing here B. You see, same thing. B by R, exponent, one is positive and negative. Now it is very important. Just look and listen very carefully. Solution of that difference, those the biologists, you have to cram it. No, there is no option. You have to just remember it, that the solution of this equation is this. Now, is very important. So suppose, again the same point. Just listen 2 minutes. Suppose it is plus, and this distance is R, and because I cannot say anything, maybe infinite is also there. I do not know what is happening in these things. So suppose I am thinking like that, same thing, I am considering that psi is equal to A minus infinite, suppose, and R is infinite, plus B infinite exponential infinite. Again, small mathematics. It is quite natural that if R is infinite, so there is no question of electrostatic attraction and other things. If there is no electrostatic attraction, other things, so no question of electrostatic potential must be 0. And if you see the mathematics, again the mathematics students can very easily understand, the exponential of minus alpha is equal to minus infinite is equal to 0, isn't it? And exponential infinite also infinite. So what we'll get here is actually, this is 0. So this part is 0. This part is already 0. This part is already 0. And you know that infinite is equal to that infinite divided by infinite. So it is B. So B is also 0. You follow this point. This point is very important. This point is very important. So only there are three simple derivation. You go to your home, see any standard book and derive it with the concept. So you will find it is not at all difficult. Not at all difficult. Of course, Debye Huckel Unsager equation is also not difficult, but there are so many substitution and other things. So deliberately I am not going to deal with that Debye Huckel or limiting law. Just it is 50% of the Debye Huckel equation, the relationship between these things. So that means when we derive this second order differential equation and its two values, so, and sometimes it is called the integration constant or whatever it is, you thought that there are two constants and there must be one thing, that this R is like that, so B is 0. See, B is 0, so that means I can write psi is equal to A by R exponential minus kappa R. Again, kappa is very important. And 1 by kappa is the thickness of the ionic atmosphere. So again, I can like that. We have already determined these things, and ultimately, after a long derivation using two great equations, Boltzmann statistics as well as the Poisson equation, ultimately we are getting a very, very simple equation, that is A by R E by KR. Now you can understand these things, that as R increases, psi must be 0, and constant B is also 0. I have already taken that. Now if it is a very, very dilute solution, so naturally summation of Ni and Zi square is also 0. So therefore, no question of the thickness of the ionic atmosphere, because it is very far from that side. Very far from that side. So simply we can write A divided by R. Last equation. And one side, whatever the chemical potential, it is only due to the Z, whatever valency, charge divided by dr. Therefore, is R cancel. So I can write A is equal to, you can use small z for board. In the most of the books, the valency is always actually, we say small. But in some cases, capital Z, but it's small, divided by D. You always see the dielectric constant is so important. Everywhere the dielectric constant is there. Valence is important and this charge is also important. So now you substitute the value of A in this equation, because when you get this solution of the differential equation, your object is to determine the value of A and B, considering that the distance from central atom to that the ions group. So R is a very important factor and automatically B is constant. So you are getting this value and then you substitute the value of A. So I am getting psi, ultimately charge density of everything. So A, in place of A, I can write Z is small, okay. Summation dr, okay. Then exponential minus kr. Again mathematics, small mathematics, you know that exponential minus, suppose this here kr is equal to x. So it is 1 minus x, like that. So what I can write like that? Finally, Zi epsilon dr 1 minus kr. So what I can write like that? Zi e dr, one case, another case Zi e k d, no r. Again I am just repeating these things. With the help of this two differential equation solution, I am determining the value of A. When I get the value of A, Z e by dr, I substitute here. So I am getting psi A d by r e kr. This exponential minus x can be written as 1 minus x, like that. So I am getting Zi dr 1 minus kr. I just elaborate these things, nothing. Zi epsilon dr, then again Zi e kr, this r cancel. So I am getting two parts. One part r is there, another part r is not there. In one part, no thickness of ionic atmosphere is there, another part thickness of ionic atmosphere is there. So same thing I am just repeating here. You can actually, it is kappa actually, for printing mistake I do not know. It is related like K. What is it, kappa? So two part, Zi e dr part and Zi e k dr part. Same. Zi valency, charge, dr, dielectric constant and radius. Second, Zi k and d. So same thing. The first term is the potential at a distance r, no surrounding ions. Because, and second term due to the ionic atmosphere. So this part is important. Here, first term is the potential at a distance r. We do not know, r may be infinite, whatever it is. I do not know. What about the thickness of the ionic atmosphere? But the second is important, where there is this concept is there. So therefore, if I write final equation, now I'm just going to again first part to just show you the my my first equation. You see that this is not complete. Why I am just showing this? Today I am just determining only first part. So Zi E dr and another is the without r is there. Sorry, just 2 minutes, because there is a possibility of some numerical problems and objective type question. You see the old question paper and other things. Sorry. Okay. So this is the final equation. That means Debye and Huckel, they finally determine this electrical potential or electrostatic potential with respect to some this part. But again there is a question, sir, what is this kappa? Everywhere it is there, dielectric constant no problem, charge no problem, valence is no problem. So it is actually, in some books it is 1 by kappa is actually, because it is derived by Debye, so in some books it is called the Debye length for any type of the things, or some books it is called the thickness of. You can measure in centimeter or you can measure in angstrom, thickness of ionic atmosphere. The last part of this today's lecture is that how do you calculate the thickness of ionic atmosphere? So the effect of ionic atmosphere is equivalent to a single charge of the same magnitude placed at a distance of 1 divided by k from ion. So an introduction to electrochemistry, I have taken these things. But sometimes what happened, there is a sometimes in some numerical question there is a possibility that how this thickness of ionic atmosphere can be calculated. So if you know the value of k, 4 pi epsilon divided by dkt summation ni, but ni is the number of moles, but number of ions, but you have to calculate the concentration. Suppose concentration is equal to moles per liter, and that is ni is equal to Ci. Now you see here we are using the Avogadro number. So in place of this I, we will write Ci n and divided by the 1000. So, and it is actually 1 by k. So our final equation will be 1 by k is equal to dkt 1000 divided by summation Ci Zi square 4 pi epsilon n, and of course half I maybe. But suppose a question is asked that what would be the effect of dielectric constant, and if you see the book of Glaston electrochemistry, there is a table showing the effect of dielectric constant, temperature and other things. So if I just solve it, you will get K is Boltzmann constant, you know, 1.38 10 to the power minus 16. Avogadro number, you know. So we will get a value 2.81 10 to the power 10 dt summation Ci Zi square. That means you can change suppose dielectric constant of water is 78 approximately, whereas dielectric constant of dioxin is 2, dielectric constant is 40, temperature is 25 degree or 27 or 30 degree. So now this possibility is very less. Nowadays nobody will ask you such type of question, but in some net and get type of things that sometimes they ask some objective type question, that what is the effect of concentration and valency on the ionic atmosphere. So the thumb rule is that it decreases. If we increase the concentration and valency, the ionic atmosphere decreases. But on contrary, if we increase the dielectric constant of the solvent from 78 to 40 or any type of the solvent, so it will increase. If we increase the temperature, the thickness of ionic atmosphere will increase. So for water and 25 degree centigrade, so this equation again modified. So 4.31 into 10 to the power minus 8 summation Ci half. So I think in this, let me summarize these things. Today I have derived the 50% of the Debye-Huckel equation, and that is the most fundamental equation, where you have seen that this electrical potential is related to the thickness of ionic atmosphere, where temperature is also there, dielectric constant is also there, and the R is also there. Now there are two conditions. One, R is very near vicinity of the central ion. Another, R is from this ions is from infinite. So one is with ionic atmosphere, another is without ionic atmosphere. But ionic atmosphere is important. And just a additional part of this Debye-Huckel theory, I have also discussed about the thickness of the ionic atmosphere. And the formula of, although it is not directly related to that part, so it is the thickness of the ionic atmosphere, and how do you calculate, if there is a possibility of any numerical question or objective type question, what would be the effect of dielectric constant, increasing concentration, valency, effect of things. So that in my second part, on Saturday or any other day, so I will discuss the next part, which is the after this, how this equation will be useful for Debye-Huckel limiting law. And third part is the Debye-Huckel equation, where I will consider, if you refer any books, there are three effects. You know that one is relaxation effect, asymmetric effect, electrophoretic effect, whole solvent is movement, and last is the frictional effect. So we monitor these three effects and will ultimately determine the Debye-Huckel equation. Thank you very much.